Hey everybody, it's Miss Berry. In this video, we are going over section 3.3. This is the last section for chapter 3, and this video is called Measures of Relative Position. So in this section, we're going to be learning about how we can calculate different statistics that tell us information about where a data point is located in a data set relative to the other data points in that data set. All right, so let's get started. Okay, so the first topic that we're going to learn about today is called percentiles, and I'm sure you've all heard percentiles used before, whether you knew that that's what you were hearing or not. Anytime you take a standardized test, your results are going to be displayed in terms of percentiles. Percentiles help us understand how a particular value in a data set compares to the rest of the data set. The definition of a percentile is that it is a measure that divides a data set into 100 equal parts. Right, so you take a data set and you divide it into 100 equal parts, and then each equal part represents a percentile. Each percentile, so if I said like the 20th percentile or the 35th percentile, each percentile is going to indicate the value below which a certain percentage of the data falls. So it's not exactly the same interpretation as percentage, but it is pretty similar. All right, so a percentile again is going to tell us the percentage of the data points that fall below a given value. All right, so the percentage of the data points that fall below a given value. So here's an example. It says when Khalil was 3 years old, his pediatrician said that he was in the 98th percentile for his height. Right, so that would indicate that 98% of other children are Khalil's height or shorter. Right, so remember our interpretation. A percentile tells us the percentage of data points that fall below that given value. So Khalil's doctor says that he's in the 98th percentile. So that means that 98% of children Khalil's age are his height or shorter. So let's write that down, or try to anyway. All right, 98% of 3-year-olds are Khalil's height or shorter. Oops, I misspelled Khalil. Are Khalil's height or shorter. Sorry guys, I'm writing with my finger on my laptop screen. I'll go get my pen in just a minute. All right, so 98% of 3-year-olds are Khalil's height or shorter. That says height. It kind of looks like weight, but it says height. It's supposed to say height. Oh gosh, I'm making it worse. Let's try this one more time. Oh yeah, that's definitely better. Okay. All right, so I'm going to show you a couple of things. I'm going to show you how to calculate a percentile. So if I give you a data point, how to calculate the percentile of that data point. I'm also going to show you, if I tell you find the 25th percentile, I'm going to show you how to find that. And then I'm also going to show you how to interpret percentiles. Okay, so we have 3 things that we're going to do with percentiles. Find the percentile of a given data point, find the data point that corresponds to a given percentile. Right, so that's sort of like those 2 questions are sort of the opposite of each other. And then the last thing that we're going to learn to do with percentiles is how to interpret them. Okay, so I know that this looks really overwhelming. I've got a lot of information on this slide. But we're just going to take this piece by piece, and I'm going to tell you what's the important stuff to write down, and I'm going to tell you what you could leave off and all that information. Okay. So it says location of the data value for the pth percentile. Okay, this is a scenario where I'm gonna ask you a question like, tell me, or actually I would probably say something more formal like find. We're gonna say something like find. Sorry if you can hear my kids in the background. Find the 30th percentile.
Look, we have this.
All right, so again, this is going to be for questions like find the 30th percentile. Now, I like to call this formula the locator formula. It's not going to tell you the answer. It's only going to tell you the location of the answer. Okay, so you can think of this as like the locator formula is what I usually call it, the locator formula. Okay. So let's read through the definition or the formula, the description of the formula, and we'll point out what parts are the most important. All right, so to find the data value for the pth percentile, again, that can be, p is just a number, it could be 30th, 25th, 74th. All right, so to find the data value for the pth percentile, the location of the data value in the data set is given by this formula. All right, so L stands for location, so the location is equal to N, that's the sample size, times P over 100. P is whatever the percentile that you were trying to find was. If it was the 30th percentile, P would be 30. If it was the 74th percentile, P would be 74. All right, so again, N is your sample size and P is the percentile. So let's talk about what do I mean by the location of the data value? Okay, so this is going to be the location is if you listed out your data from smallest to largest, L is going to be, if you count, okay, first data value, second data point, third data point, fourth data point, fifth, if I could count. So first, second, third, fourth, fifth. So L is going to be that actual location of the data value. So you will start at the beginning and you'll count up to whatever that location is, and that's the answer. All right, so it says, when using this formula to find the location, you must be sure to follow these two rules. So here's what could happen. Whenever you plug in all your numbers here, you might get out a decimal value. Okay, every once in a while you'll get a whole number value, but most of the time you're going to get a decimal value. All right, but here's what you do if you get a decimal, and then here's what you do if you get a whole number. All right, so if the formula results in a decimal value for L, I know that looks like I, but it's actually a lowercase l. So if the formula results in a decimal value for L, the location is the next larger whole number. Okay, so let's say that you plugged in your numbers and whoa, I lost my spot here. Where am I at? Okay. Sorry, I couldn't see where my pen was. All right. So let's say that you plugged in all your numbers and you got L equals 7.71. You would go to the next larger whole number, right? So you're going to go up to the 8th position. Let's say that you plugged in your numbers and you got 2.3. Even though your rounding rules would tell you that this rounds to 2, this rule in the locator formula tells you that you have to round up to the next larger whole number, which is 3. All right, so you would go to the 3rd position or the third data point in your ordered list of data points. Okay. So no matter what your standard rounding rules tell you, the locator formula says if you get a decimal value, go up to the next larger whole number. Okay. Now let's look at what happens if we end up with a whole number here. So if you end up in one of these rare circumstances where you end up getting a whole number for L, then the percentile's value is going to be the average of the data value in that location, so whatever you got for L, right? So let's say that you plugged in all your numbers and you ended up getting L equals 8, perfect whole number. Right, this locator formula is telling you, okay, well, you go to the 8th position in the data set and take the average of that data value in that location and the data value in the next larger location. Right, so you're going to go to the 8th position, record that data value, then go to the 9th position, record that data value, and then take the average of those two. Okay. All right, so now that we know how the formula works, let's point out the important parts. All right, so of course, the actual formula itself is important. All right, I'm trying to circle that. Let's see if I can. There we go. All right, the formula itself is important. You need to know what N and P are. P is whatever the percentile is. Oh my gosh, it's so hard to draw a straight line on here. All right, P is whatever the percentile is. N is the sample size. All right, and then you have to know what to do in each of these scenarios. So make sure you get rules 1 and 2 down. All right, so you could probably shorten these rules somehow. That might be a really good way to incorporate AI here is you could type these rules in and then say like, please shorten these rules so that they can fit on my formula sheet, something like that. All right, so shorten the formula, shorten the rule so that it's easier to understand or something like that. Okay, all right, let's practice this. All right, so here you're looking at a stem and leaf plot. This is the stem and leaf plot for final exam grades of 73 students from a previous semester. I think I actually made these numbers up. And it wants us to find the 10th percentile and the 52nd percentile. All right. So, whoops, drew on my data set. Oh gosh, drawing on it even more. Okay, there we go. All right, so first let's just start by taking a look at our stem and leaf plot. So the highest grade here would be a 105. The lowest grade, someone made a 5, someone made a 9. Here the stem of 1 tells us that this person made a 12, a 15, a 17, another 17, a 19. Then in the 90s, jumping down to the 90s here, we have a 91, we have a 93, another 93, 94, 96, 98, 98, 98. Okay, so just a quick reminder of how you read a stem and leaf plot. All right, so we're going to start by finding the value of the 10th percentile. All right, so remember, we're going to use the locator formula. And the locator formula is only going to tell us the location of the answer. It doesn't tell us the actual answer. All right, so let's write down our formula. L equals N times P over 100. Very simple formula, just a complicated interpretation. N is our sample size. Luckily, we don't have to count these, but we were told that there were 73 students in this data set. Right, times P is the percentile, that's 10. It was the 10th percentile we were trying to find, right, over 100. All right, I'm going to plug this into my calculator. I want you to grab your calculator and do the same. We'll make sure we get the same value. All right, so 73 times 10 over 100 is 7.3. 7.3. All right. And y'all remember what we do when we get a decimal. Y'all remember whenever we get a decimal value for L, we always go up to the next largest whole number. Right, so you go up to the next largest whole number. So we're going to go to the 8th position, I'm going to call it. Now this isn't the answer. 8's not the answer. 8's the location. All right, so let me switch to my laser and let's start counting. This is our first data point. These are the stem and leaf plot is nice to have here because they're already listed in order from smallest to largest. All right, so first, second, third, fourth, fifth, sixth, seventh, eighth. All right, so in the 8th position, we have the grade of 20. All right, so we'll say value. It says find the value of, so I'm writing value equals 20. Whoa, let me try that again. Goodness gracious. Value equals 20. All right, so if you scored a grade of 20 on the final exam, then you could say, I scored in the 10th percentile. So that, again, that interpretation means 10% of students scored my score or lower. All right, so 10% of students scored a 20 or lower. All right, let me write that interpretation down. 10% of students scored a 20 or lower on the final exam. FE final exam. All right, so that would be the interpretation of that percentile. Okay. All right. Now I'm going to give you a little less guidance on this next one. I'm going to help you set it up, and then I'm going to be quiet for a minute and let you figure it out on your own, or let you try to figure it out on your own. All right, so L equals, we're trying to find the value of the 52nd percentile. So it's N times P over 100. We already know that our sample size is the same as before at 73. So N is 73. This time the percentile we're trying to find is 52. So that's 52 over 100. All right, take a second, type that in your calculator. All right, what number are y'all getting? I'm getting 37.96. Okay, and my rule tells me that if I get a decimal value, I'm always going to round it up to the next whole number, which is 38th. So we're going to the 38th position. All right, remember that's not the answer, that's the location of the answer. All right, so now you're going to go to your data set. You have a couple of options here. You can either start from the bottom and count to 38, or if you prefer, if it was a really big number, say it was like 62 or something like that, it might be better to start at the 73rd and count down and say like 72, 71, 70, 69, 68. So you can go that way too. I'm going to count from the bottom. I already know that 20 is in the 8th position, so I'm going to start from there. All right, so y'all count as well, and we'll make sure that we get the same thing. So I'm going to count silently. Okay, I'm getting 67. in the 38th position. I'm going to pause real quick and then I'm going to count that one more time. But right now I'm getting 67. Okay, I just counted again and that was correct. So I got a 67 for the value. All right, so the value equals 67. And then you don't have to do this part, but I'm just going over here just so we understand what that means. I'm going to come over here, or I'm going to try to anyway. All right, I'm going to come over here. There it is, okay. And I'm going to write the interpretation. All right, so 52% of students scored a 67 or lower on the final exam. And you can use this sentence as kind of like a little template. All right, so you could say, okay, I'm always going to start by listing whatever the percentile is, right? So I'm going to start with whatever the percentile is. Here it was 52nd. So 52% of, then insert whatever your data set's about. If it's about sunflowers, if it's about students, if it's about patients, whatever your data set, whoever you were surveying. Oops, what? I don't even know what happened to my sentence there. I lost part of it. All right, 52% of students scored a 67, or that's supposed to say lower, on the final exam. I'm not sure what happened there. All right, so again, talking about the little sentence template. All right, so you start with whatever your percentile was. Here it was 52 of blank, whatever your data set is. And then this number is always your value. So that's what you just calculated over here. And then the or lower, that's going to be the same every time. And then the last part, of course, is going to change based on your data set. Right, so sort of like a little template that you can kind of just fill in the blank. That might be a good idea to write an example sentence of how you would interpret one of these percentiles. So that might be something good to add to your formula sheet. Okay, so now we are looking at the sort of like what I would think of what I would think of as the opposite formula from the locator formula. So this formula is going to tell you, okay, if I have a particular value in a data set that I'm looking at, say I gave you that stem and leaf plot and I know that I scored a 93 on the exam. All right, so if I know my score on the exam, how can I calculate my percentile? All right, so that's what this formula does. It says, let me get my little laser up here. All right, so the pth percentile of a particular value in a data set is given by this formula. All the variables mean the same thing. All right, so P means the percentile. L is the location, which here they're defining as the number of values in the data set that are less than or equal to the given value. All right, so you count all the way up to the number, and then N is the sample size. All right, so P equals L over N times 100. It's really just an algebraic rearrangement of the previous formula that we saw. All right, so P is the percentile rounded to the nearest whole number. All right, that's important. P is the percentile rounded to the nearest whole number. L is the number of values in the data set that are less than or equal to the given value. So you have to count all the way up to that given value. And N is the sample size. All right, so here we have an example. It says in the data set from the previous example, one student scored a 71. In what percentile is this score? All right, so here's our data set. There's our 71. All right, so we need to start with the person that scored the lowest. In this case, it would be a 5. And we need to count all the way to 71 to figure out what's the location of that data value. All right, so if you count all the way up to 71, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. Right, so it's the 42nd data value in our ordered list. All right, so L becomes 42. N is our sample size. We already knew that 73 people took this final exam. All right, so now grab your calculator, plug that in. 42 over 73 times 100. You don't have to do anything fancy when you're plugging that in the calculator. It doesn't need any parentheses anywhere. All right, that gives us 57.53. Remember, they told us that we're supposed to round the percentile. We're supposed to use our normal rounding rules. All right, so for 57.53, we would round up since our decimal here, the 0.53, that is larger than 0.5. So we're going to say that's approximately the 58th percentile. So if you scored a 71, you would say, okay, I scored in the 58th percentile. That means that 58% of students scored a 71 or lower on the final exam. All right, that's our interpretation. All right, so next we're going to talk about quartiles, which are really just special percentiles. So quartiles are the special percentiles that help us divide the data set into 4 equal parts. Each of those 4 parts is going to contain 25% of your data points. All right, so we have special symbols for our quartiles, and we're going to see those in our calculator whenever we look at the output for our one variable statistics. You've probably seen the symbols before. Q1 is the first quartile. It's also known as the 25th percentile. Next, we have Q2. This is called the second quartile. It's more frequently referred to as, as the median, but it's also known as the 50th percentile. So this is like the middle value in your data set. So Q2, also known as the median. Q3 is the third quartile. It's also known as the 75th percentile. There's no Q4. That would just be the largest value in your data set. So we do not typically refer to Q4. All right, so you can use quartiles for a lot of different things, but one of the main things that they're used for is to, there's a rule that we have in statistics that allows us to determine, sort of like a set rule for how do we determine if there is an outlier in your data set. So that is the one of the main usages of quartiles. All right, but let's do some examples on calculating quartiles. All right, so we're going to find the quartiles for our final exam data set. All right, so here's our stem and leaf plot. Our quartiles are Q1, the 25th percentile, Q2, the median, or the 50th percentile, and then Q3, the 75th percentile. All right, so in this scenario, we are trying to find a given percentile, so we need to use the locator formula. All right, so if you're asked to find the pth percentile, you need to use the locator formula. All right, so let's pull that formula up. L equals N times P over 100. Remember, L is the location, N is the sample size, P is the percentile. All right, so N is 73. We already knew that. P is 25 in this case. All right, so go ahead and plug that into your calculator. 73 times 25 over 100. All right, I'm getting 18.25. All right, and remember with the locator formula, the rule is if you get out a decimal value, you're always going to round it up. You're going to ignore rounding rules. You're always going to go to the next larger whole number, which in this case is 19. All right, so we're looking at the 19th value in our data set. All right, so let's start counting. We already know that 20 was the 8th, so let's start from there. All right, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Right, so 40 is the 25th percentile. All right, so Q1 is 40. All right, so we'll try to remember that 40 is that first zero there. That's the 19th value in our data set. All right, so next we are finding Q2, also known as the median. This is the value that splits the data set in half to where half of the data are lower than this value and then half of the data are larger than this value. All right, so you could also use the same, method of how we found the median back in chapter 2, where you just mark off one from each end until you get to the very middle value, but this way might be a little faster. All right, so plugging in our numbers, L equals N times P over 100. So N is 73, P is 50. All right, so it's the 50th percentile. So P is 50. Let's write that off to the side. L equals N times P over 100. Whoops. N is 73, P is 50. All right. Go ahead and plug that into your calculator. 73 times 50 over 100 is 36.5. We're always going to round up. Our locator formula requires us to round that up. That's a little arrow there. It's kind of hard to see. It's under the 100. But we're going to round that up to the 37th position. All right. 40 was the 25th. Oh, is that right? No, that's not right. Okay, I'm going to have to start over. All right, I'm going to pause the video and that way I'm not using up our time to count silently. All right, so I'm going to start at 5. and then I'm going to count all the way to 37. I want you to do the same, and we'll make sure we come up with the same value. All right, so if you count up to the 37th position, the value is 67. 67. All right, so again, the interpretation there is that if you scored a 67, on the test, we would say 50%. Ooh, where'd my pen go? Ah. Oh my gosh, what happened? 50% of students scored a 67 or lower on the final exam. All right, and next we're going to find Q3, or the 75th percentile. I'm going to go through this one a little faster since this is like the 5th time we've done this. All right, so using our locator formula, 73, that's again, our formula is L equals N times P over 100. All right, so N is 73. That's our sample size. Our value for P is the percentile is 75. 73 times 75 over 100 is 54.75. That tells us that we're going to look at the 55th position in our data set. It might be faster to count down from 73 in this case. If you wanted to start here at 73 and say 72, 71, 70, 69, 68, 67, 66, 65, 64, 63, 62, 61, 60, 59, 58, 57, 56, 55. All right, so an 85 would be the 75th percentile. All right, so we would say 75% of students scored an 85 or lower on the final exam. All right, this also tells us, you can sort of use this to tell you information, other types of information, like for example, if we said that 75% of students scored an 85 or lower, that would mean that 25% of students scored an 85 or higher. Or I guess technically it would be 25% of students scored above an 85 would be the opposite of that statement. All right, so while we're on the topic of quartiles, we're going to talk briefly about the 5-number summary. All right, so 5-number summary is a quick way that you can describe a data set without having to look at all, say, 73 final exam scores. All right, so a 5-number summary is going to tell you the minimum value. It's going to tell you the first quartile, the second quartile, aka the median, the 75th quartile, and then the maximum value in the data set. All right, so we're going to come up with our 5-number summary for the final exam data. We already know that the minimum is 5, and we know that the highest score was 105, and then we just found Q1, Q2, and Q3. All right, so we've got our 5-number summary for our data set. So you could quickly look at this and say, okay, well, students scored between a 5 and 105, so we've got a really big spread there. 25% of students scored a 40 or lower, 50% of students scored a 67 or lower, 75% of students scored an 85 or lower, and then our maximum was a 105. All right, so we talked before about how you can use quartiles to determine if you have outliers or really extreme values in your data set. And part of that formula, which I'm not sure that we'll have to cover that in this class, but you may see it in a future stats class. But part of that formula involves what we call the interquartile range. And the interquartile range tells you how spread out. All right, let me try to write this down here. Tells you how spread out the middle 50% of the data set is. How spread out the middle 50% of the data set is. And it's super easy to calculate. It's just Q3 minus Q1. So the 75th percentile minus the 25th percentile. And we abbreviate interquartile range as IQR. All right, so this sort of eliminates those extreme values like we saw on the last page with our final exam scores. Like we had someone score as low as a 5 and then other people scoring as high as a 105. So that sort of takes those folks, those extreme low scores or the extreme high scores, and it throws them out of the data set. And it says, let's just look at how are the folks that are in the middle of the data set? How spread out are those people? All right, so let's look at an example with interquartile range. All right, so for our final exam data set, this was our 5-number summary. Again, remember, this is the minimum, this is Q1, Q2, Q3, and then the maximum. So if we were to calculate the IQR here, that would be 85 minus 40 is 45. So you could say the minimum, or excuse me, the middle 50% of the data set. So the middle 50% of our students are spread out by 45 points. So that's quite a large spread for a test, I think. That's like over 4 letter grades. So yeah, that's a pretty big spread. So that might tell you, okay, we have we don't have our values clustered together very well, so maybe we want to reconsider some of the questions on that final exam. All right, so box plots are another type of way that we can display our data. And once you know how to read a box plot, they're very easy to read. They are completely based on the 5-number summary. So they're really easy to construct, really easy to read. And they just sort of give you a great visual on how the data set is spread out. All right, so it says write a 5-number summary for each of the box plots below. If you look at our box plots, the way that your textbook writes them, it is super easy to grab a 5-number summary off of it. It's just 1, 2, 3, 4, 5. You just read them from left to right. All right, so we've got Q1 in the first position. All right, so these are called the whiskers of your box plot. So the left whisker is going to extend out to to the minimum. All right, then the whisker goes along here. The box is going to start at Q1, so 60 is Q1. All right, we go along in our box. Bam, that next line is the median, or Q2. The box ends at Q3. And then your right-hand whisker is going to extend out to the maximum value. Okay, so they have different colors here, so you can kind of see, okay, this is the, the 25th percentile to the 50th percentile, so how spread out is that? Whereas the 50th percentile to the 70th percentile is kind of close together. So it kind of gives you an idea of how the data values are clustered in there. All right, so let's write a 5-number summary for these. All right, so for our first data set, I made this little table, minimum, Q1, Q2, Q3, and then maximum. And again, we know that Q2 is also called the median. All right, so for our first data set A, our minimum is 52. Q1 is 60. Q2, where the median is 79.5. And then Q3 is 86. And then our maximum is 94. All right, and then starting on our second data set B, our minimum would be 45, so that whisker extends out to 45. The box plot begins at 61, so that's Q1. the median, or Q2, is 71.5. That's where that line is drawn where the color changes. The box ends at Q3, which is 85, and then our maximum, that's where our whisker extends out to, is 89. All right, so again, the box plots give you a great view of the data set as a whole, even though it's only got 5 numbers represented here. And how we can interpret this is that if the median is sort of dead center inside of your box, then you could say that the data set is somewhat symmetrical. So you can see in data set B is definitely more symmetrical than data set A. But our whiskers are what tell us how the data set is skewed. So if you have a longer whisker on the right, like the one up here, it is just, I think it is just slightly longer if it is longer at all. But if you have a longer whisker on the right, then the data is going to be skewed to the right. If you have a longer whisker on the left, like this one here, then the data set is going to be skewed left. Right. So the longer whisker on the left tells us that this is skewed left, which means the peak is on the right. All right, and then finding the standard score. Your book calls this a standard score. I'm always going to call this a z-score. All right, so this is like if you want to standardize your data set, what this can help you. If you have like sort of complicated values in your data set, you can do what we call standardizing and put them all into a standard form that makes them a little bit easier to work with. Whenever your values are standardized, that's going to give them a mean of 0 and a standard deviation of 1. All right, but we'll talk about that more whenever we get into the next chapter. This is our formula for the z-score or the standard score. In general, the formula is just value minus mean over standard deviation. So whatever the value is minus whatever the mean is divided by the standard deviation. All right, so if you Google standard score or z-score, you're going to see a formula that looks slightly different than this. It's just the one that involves the symbols. So you might see it written like this, x minus x bar over s, or you might see it written like x minus mu over sigma. But I like writing it like this because this applies to any scenario, whether it's the population or a sample that you're dealing with. So I like writing it with the words instead of the symbols. All right, so it says if the mean score on the math section of the SAT is a 500, okay, that's the mean, with a standard deviation of 100, okay, that's the standard deviation, what is the z-score for a person who scored a 630? That's our value. All right, so we're going to plug in our numbers. Value is 630. Mean, they said, was 500. Standard deviation is 100. All right, so 630 minus 500 over 100. Now, when you're plugging this in the calculator, you can either do this in 2 steps. So do the numerator first, then hit enter, and then divide by 100. If you want to do it all at one time, just make sure you put parentheses around that numerator. Right, so if you don't put parentheses around the numerator and you try to do it all at one time, your calculator is going to think you're doing something like this. They're going to think you're doing, okay, 630 minus 500 over 100. Right, so they're going to just think you're dividing the 500 by 100. Right, so make sure you put parentheses around that numerator, or you just do it in 2 steps. All right, 630 minus 500 over 100. 1.3. All right, so if your z-score is positive, let me write this down here. If z-score is positive, that means the value was above the mean. or larger than the mean. And then on the opposite end, if your z-score ends up being negative, that just means that the value was below the mean. Okay, so how were you going to use this information? If you're given some z-scores and you're supposed to be interpreting them, the ones that are positive, you're going to say, okay, I know that those people scored above the mean, or their heights were larger than the mean, whatever the interpretation is of your variable. If that person's z-score is negative, then that just tells you, okay, that person was below average. Okay. All right, so here's a great question. I usually put a version of this question on the test as like a bonus. It says 3 potential employees took an aptitude test. Each person took a different version of the exam, and the scores are reported below. All right, so we've got Nico, Justin, and Tara, and we're supposed to figure out who actually performed best on the aptitude test. So these 3 potential employees, say that they each went out and took some kind of test, and they each took a different type of test, but it was measuring the same thing. Just like how whenever you're getting into grad school, there are different types of tests you can take, but they all sort of measure something similar. All right, so in Nico's case, he got a score of 88.3, and his test had a mean of 66.2 and a standard deviation of 13. Justin got a score of 226.2, much higher, but his test had a mean of 216 and a standard deviation of 17. And then Tara got a score of 7.97, very low compared to the other two, but her version of the test had a mean of 7.2 and a standard deviation of 0.7. So what we can do is we can standardize all of these scores, and then that puts them on the same scale. All right, so if we standardize their scores, then we can just compare their z-scores, and we can say, okay, well, that person scored the most above the mean, the most standard deviations above the mean. So that person scored the best. All right, so we're going to calculate z-scores for Nico, Justin, and Tara. All right, so Nico, Justin, and Tara. All right, so for Nico, remember we're doing value minus mean. Let me write that up here. Z equals value minus mean over standard deviation. All right. For for Nico, he got an 88.3 on the test. His version had a mean of 66.2, so value minus mean over his standard deviation, which was 13. All right, so go ahead and plug that in your calculator. Once again, either do that in 2 steps. So do the numerator, hit enter, then divide by 13, or make sure you're putting parentheses around that numerator. All right, so I went ahead and calculated the numerator. 88.3 minus 66.2 is 22.1. So 22.1 divided by 13 is 1.7. All right, so I want you to pause the video now. I want you to pause the video and calculate Justin's z-score and Tara's z-score. All right, so just mimic what we did here with Nico's. Calculate Justin's z-score. Remember, he got a 226.2. His had a mean of 216 and a standard deviation of 17. And then for Tara, she scored her value was a 7.97. Her mean was 7.2, and her standard deviation was 0.7. All right, so please pause the video and do that on your own. All right, so Justin's z-score, 226.2 minus 216 over 17. The numerator simplifies to 10.2, and his z-score is 0.6. So right now, Nico's in the lead. He's got the higher z-score, so that means he scored the most standard deviations above the mean so far. All right, now for Tara, 7.97 minus 7.2. All right, so that's value minus mean. Her standard deviation is 0.7. Numerator simplifies to 0.77. If we divide by 0.7, that gives us 1.1. So she scored better than Justin, but she didn't quite catch up to Nico. So Nico performed the best on the aptitude test. All right, guys, that's everything for this video. If you have any questions, please let me know, and I'll see you next time.